All right, so last time we ended with uh, figuring out the tangent with sine over cosine. So today I'm just going to talk about the sum angle formulas and difference angle for sine and cosine, and then I'll talk a bit about the inverse trig functions. So first of all, I just want to show you something interesting. So remember when we did tangent, we drew this triangle. So just putting it off to the side, the small triangle has sides cosine, sine, and hypotenuse 1. When we extended the triangle to tangent, this side was tangent. This whole side is 1 because it's 1 on the unit circle. And so one thing to notice is that we'd actually find the hypotenuse of this big triangle, right? Since these are all right triangles, we can figure out by doing the Pythagorean theorem. So 1 squared plus tangent squared is equal to the hypotenuse squared. So this is actually a Pythagorean identity. This is actually equal to secant squared. Remember from last time. So in fact, the hypotenuse is actually secant. So it's a nice kind of visual representation of secant as well as tangent. So just wanted to start with that. So now we want to prove a relationship between the sine of a double of the angle. So what is sine of a sum of two angles? So here's how we're gonna prove it. So we're gonna use what we did last time, which was that sine of an angle is equal to the side opposite divided by the hypotenuse. So why don't we draw a triangle? Angle theta, right triangle, and let's give maybe some letters. Let's say this is A. Let's say this is B. Let's be C. And then from A, I'll also draw an angle phi. And I'm going to extend BC up to meet that. And let's call this side D. So what is sine of theta? We know by the opposite of hypotenuse, it's equal to BC divided by AB. By this construction, we don't know what sine of phi is because this is not a right triangle, but we do know that sine of theta plus phi is equal to the full length DC divided by the hypotenuse of the big triangle DA. However, we don't know what these lengths are. We don't know what DC or DA are. So we're going to do some things. So let's take AB and then continue the line. And from D, we'll draw a line that is perpendicular to this extended AB. So one thing we know about triangles, so remember that the angles in a triangle add up to 180, is that let's look at this triangle ABC. We have angle theta, we have angle 90, then we have this mystery angle here, and this is equal to 180. So solving for x, we get x is equal to 90 minus theta. So this angle here, this is true for all right angles, is that if you know one of the angles in a right triangle, you know all of them. So this angle must be 90 minus theta. And some thing about angles is that vertical angles are equal. So what are vertical angles? That if you have two lines that intersect, the angles opposite around the intersection are equal. So this angle is also 90 minus theta. Now, if that's true, that means that this angle must be theta. So we've constructed a triangle that has also the same angles. These are similar triangles. So just to clean it up, I'll erase the 90 minus theta. So notice that, so we have in the first triangle, sine of theta was equal to BC over AB. And in this triangle, sine of theta is equal to, we have this letter, let's call this, what's the next, E. We have BE over hypotenuse BD. So both of these values are the same, BE over BD and BC over AB. So one more thing we're going to do for the proof is that we're going to draw a perpendicular from E, and let's call this F. So the goal is to find a relationship of sine of theta plus phi. So we want to find something that's equal to DC over dA. So one thing, one last thing we're going to do is that we're going to draw a line from E that's perpendicular here, and let's call this what, G. So we have this triangle DGE. And we also have another relationship of sine that in this triangle DGE, that sine of theta is also equal to what, GE over DE. So yeah, another thing we can say about sine of theta. Okay, so notice that DC, this big line, can actually cut up DC. It's actually equal to DG, this line that we just drew, and then plus the remainder, GC. Now, since we care about sine of theta plus phi, let's divide everything by dA. So now we're going to do a trick, is that we're going to multiply these fractions by 1. So now which one do we want to, let's see, which one do we want to multiply? Oh yeah, actually one thing we can say is that, just as a fact, that this GC value, it's not really nice because it's not part of a triangle, right? However, this length EF is equal to GC, so we can just replace it by EF, and that is part of the triangle, so that's a little bit nicer. Say GC, DG over DA plus EF over DA. So what we're going to do, let's multiply this value over here by DE over DE. And why we care about that is that that is a hypotenuse of some triangle, which might have some relationship to sine. And, or let's see, do I want to do that one? That is a length that we care about, but I'm also going to, actually I want to multiply this one by DE over DE. And to the other one, we can multiply this, we'll multiply different length, multiply this one, AE over AE. Okay, so now we can rearrange the fractions and get dg over de and dE over dA. We get EF over AE and AE over dA. So why do we do that is because notice that each of these ratios, for example, dg over dE, dg over dE, those are ratio sides in the triangle. In particular, what is it? So take the angle, this angle here, theta, dg divided by de is actually the cosine. That's cosine of phi, of theta. How about de over dA? dE over dA, well, that is sine of phi. How about EF over AE? EF divided by AE, that is sine of phi, or sine of theta, sine of theta. And AE divided by dA, AE divided by dA, that's cosine of phi. So this is all equal to dC over dA, dC over dA, which was cosine or sine of the sum. So now we have some angle formula. So if I see sine of theta plus phi, I can rewrite that as cosine theta sine phi plus sine theta cosine phi. All right, anybody have any questions about that? Okay, so we can use this fact. Let's rewrite it. Sine of theta plus phi is equal to, let's say sine of phi cosine of phi plus sine of phi cosine of theta, just kind of rearranging some things. And let's suppose this is true. Suppose theta was equal to phi. Then you can have sine of theta plus theta, which is equal to sine of 2 theta. And we can still write this out as sine of theta, cosine of theta, plus sine of theta, cosine of theta. It's actually 2 sine of theta, cosine of theta. So here's a double angle formula. So if we see sine of double of an angle, it's 2 sine theta, cosine theta. Now, before moving on to cosine, let's remember some fact about triangles. Okay, so if this is theta and this is 90, then this must be 90 minus theta. So let's take theta, and we know that sine of theta is equal to the opposite over the hypotenuse, right? Opposite over hypotenuse. But notice that cosine of 90 minus theta is the adjacent over the hypotenuse, adjacent to this angle. So it's also the same as sine of theta. So this shows that sine of theta, it's actually a direct relationship between sine and cosine, is actually cosine of 90 minus theta. So this is this relationship is something called cofunction. So cosine is the cofunction to sine. And that's because it has this relationship that if you differ the angle by 90, then you get sine. Okay, so let's use this fact. Oh, so, and by the way, it works both ways, right? Notice that cosine of this angle is the adjacent divided by the hypotenuse, which is the same as sine of this angle. So that's also true that cosine of theta is equal to sine of 90 minus theta. So it works both ways. All right, so let's say if we want to come up with a formula for cosine some angle, cosine of theta plus phi. What can we do? Well, we don't have a sum angle formula right now, but we do know that cosine is equal to sine of 90 minus theta plus phi. And we do have a sum angle formula for sine. Well, it's, well, actually, let's write this a little differently. Let's say this is plus negative theta plus phi. Negative theta plus phi, because we didn't talk about difference, but it works the same way. So we have sine of 90, cosine of negative theta plus phi, plus sine of negative theta plus phi, cosine of 90. Now those who are here, can you tell me what sine of 90 is, if you remember? It's like we dropped down to 3 people, but if you don't want to participate, it's fine. Participate, that's fine. Sine of 90 is 1, and cosine of 90 is 0. Yeah, so what we're left over is we have cosine of negative theta plus phi, and then plus sine of negative theta plus phi. Let's see. Oh, so no, this is 0. Oh, oops. Let's see. Is there a different way of doing this? Actually, I thought this was the way to prove it, but I guess it's not, because we didn't really get anywhere. So maybe next time I'll go over the proof for cosine, but I'll just give it to you then. Cosine of theta plus phi is cosine of theta cosine of phi minus sine of theta sine of phi. So sorry about that. Next time I'll go over the proof. I thought it was straightforward from cofunctions, but you don't have to know the proof, but I wouldn't feel satisfied just giving you a formula like this. But you can do the same thing, is that if you have cosine of double, then if you replace these with the same angle, you have cosine theta cosine theta minus sine theta, or sine theta, or cosine squared of theta minus sine squared of theta. So these are the cosine values. So now you might want to be curious about how about the difference of two angles? So if I'm thinking about sine of theta plus minus phi, then, well, I can just treat this as sine of theta plus negative phi. So by using the formula we came up with, it's sine of theta cosine of negative phi plus sine of negative phi cosine of theta. So the big thing we need to figure out is what is the relationship between sine and cosine of a negative angle. So let's figure that out. So let's look at the unit circle. And let's pick an arbitrary angle here. We know that the point here is cosine of theta, sine of theta. My definition of sine and cosine. Now, what we can do is let's take this point and let's reflect it over the x-axis. So by the symmetry of the reflection, this angle must be the same as this angle here. But by convention, since it's going in the opposite direction, we'll call this negative theta. And this point is cosine of negative theta, sine of negative theta. However, does anyone remember the relationship when you reflect over the x-axis? So what is the relationship between the x values when you reflect, and what's the relationship between the y values when you reflect? I mean, you could just kind of look at the picture. Well, the x values don't change, right? But the y values get negated. So cosine doesn't change when you negate a number, an angle. But when you negate the angle for sine, it's the negative of the original. So this is sometimes called the symmetry of sine and cosine. So cosine is called even, is an even function. So if you don't remember what that means, it just means that when you plug in a negative number or a negative, if you plug in the negative of something, it's the same as plugging in the positive of something. And sine is an odd function, which means when you plug in the negative of something, you get negative of plugging in the positive something. So we can use this property to look at the difference formula. So we just showed that cosine was even. So that means that sine, or this turns into sine theta, but cosine of negative phi is just cosine of phi, because we just showed it was even. Now sine of negative phi, well, we just showed that sine was odd. So this must mean negative sine of phi cosine of theta. So there's our formula for the difference of two angles. So for cosine, do the same thing. You treat it as adding the negative, and we have cosine of theta, cosine of negative phi, minus sine of theta, sine of negative phi. So cosine is even, so it's cosine theta, cosine phi, and then sine is odd, so it's plus now, sine of theta, sine of phi. So again, sorry for not coming up with a good formula or a proof for the sum of angles for cosine, but so now we have formula for the difference. Okay. I won't do the halves, the half angle formulas. I'll give you just the idea of it. So we know that, so let's say sine of 1/2, sine of 1/2 theta, Well, what would, so like, if you said let 1/2 theta equal phi, then see, sine of 2 phi is the same as sine of theta. So you can write this as, we know the double angle formula for sine is sine of phi sine of, or cosine of, sorry, it's 2 sine of phi cosine of phi. But if, sorry, that's not what I want to do. Let's see. Okay, yeah, so notice that sine of 1/2 theta, well, if I want to look at sine of theta, what is the relationship? Is that theta is twice the double of 1/2 theta. So, so essentially, we can use the double angle formulas to figure out the half angle formulas. But I guess I won't go through that. But I guess the main thing I wanted to kind of get to for this one was the inverse trig functions. So one thing, just recall that the inverse of a function in general exists when a function is 1-to-1. So 1-to-1 means like passes the vertical horizontal line test. So why is that true? Well, what does the inverse function mean is that if you have like y is equal to f of x, the inverse of a function means that if you plug in the outputs, that you should get the inputs back. So why must a function be 1-to-1? Well, suppose it wasn't. So a function not 1-to-1. That means there exist 2 x values that both give you the same y value. So if the inverse existed, it would output 2 x values, but that means it's not a function. Right? A function is something that when you have an input, you only have one output. So this is explicitly the reason why the horizontal line test is something you check for the inverse of the function. And again, why is that? Is that the horizontal line test counts for your y values. So if you have 2 y value, if you have the same y value for 2 x values, then inverse does not exist. Okay, so why would we even be talking about inverses for sine and cosine? They're like the least 1-to-1 looking functions, right? For example, like sine of pi over 4 is equal to radical 2/2. However, sine of 3 pi over 4 is also equal to radical 2/2. This is in the unit circle. And if you don't know those values, that's fine. I think the point that there are multiple same values for sine is kind of clear. It's because if you draw a horizontal line and on the plane, these are all the same y values. So clearly, that means that sine, this y value is sine of theta, and this y value is sine of this angle. So you have the same y value, so clearly sine is not 1-to-1. So one thing that we can do is, since sine is not 1-to-1, our question is, let's find an interval where sine is 1-to-1 and has all outputs. So the idea is that I want to find an interval that has all the y values and only one y value per x. So one choice is this half circle. So if I only take angles in this half circle, notice I only get one y value per x value per angle. So one y value per angle theta. So for this angle, this is the y value. For this angle, this is the y value. For this angle, this is the y value, etc. And notice in this interval, I encompass all possible y values of sine. So what we can do is say, let's restrict sine to look at only negative pi over 2 to pi over 2. So so down here is negative pi over 2, and then I sweep up to pi over 2. So in this interval, sine is 1-to-1, and it hits all possible y values. Okay, so why is this nice? Is that when we define the inverse of sine, we'll say let's only look at these as my outputs, and then when I talk about the inverse, I can give you the angle per output. So let's look at domain negative pi over 2 to pi over 2. Sine is 1-to-1 here. So let's define arc sine as the inverse of sine. So essentially you input outputs of sine, and it outputs inputs of sine. So for example, if I have arc sine of 0, Well, I should say, let's say, it outputs inputs of sine in the range negative pi over 2 to pi over 2. So when I say arc sine of 0, what I'm saying is what angle in negative pi over 2 to pi over 2 is such that sine of that angle is equal to 0. So there's only one angle in this interval where sine of 0, where sine of the angle is 0. So arc sine of 0 must be 0. 0 degrees is the only angle where sine of 0 is 0 in the interval negative pi over 2 to pi over 2. So you can do other ones. Arc sine of 1. There is only one angle that gives you arc sine of where sine is 1, which is pi over 2. Arc sine of negative 1 is negative pi over 2. And again, since sine of negative pi over 2 is equal to negative 1, we have arc sine of radical 2 over 2. There's only one angle that gives radical 2 over 2, which is pi over 4. Arc sine of radical 3 over 2, which is pi over 3, etc. So let's do the same thing but for cosine, and we'll actually also do tangent. So let's look at arc cosine. Now, something different about cosine is that I can't use the same interval as I did with sine. Because if I want to look at the x values, and to make cosine 1 to 1, notice that in the interval negative pi over 2 to pi over 2, well, there are multiple x values for the same angle. This angle is the same x value as this angle. So I can't use negative pi over 2 to pi over 2. So I'm forced to choose a different interval. So one that I can pick is this interval here. Notice that at every angle in this interval, I'm only getting one x value. So this has this x value, that x value, that x value, that x value, that x value. So in 0 to pi, cosine is 1 to 1 and encompasses all x values on the unit circle. Okay, so we can do the same thing. We can figure out values of arc cosine of 0, let's say. Well, what is the only angle in 0 to pi where cosine of what is equal to 0? The only answer is pi over 2. Arc cosine of 1. What is the only angle in that interval that outputs 1? It's 0. Arc cosine of negative 1. What is the only angle in that interval that gives you negative 1? It's negative, or it's positive, it's pi. We can do what is arc cosine of radical 2 over 2? It's pi over 4, etc. So one thing to note about arc cosine an arc sine of x is about the domain. So what can you plug in into arc cosine and arc sine? Well, what is the only answer? You can only plug in outputs of sine and cosine. So if something is not an output of sine and cosine, you cannot plug it into arc cosine, arc sine. So for example, arc cosine of 2. Well, is 2 an output of sine or cosine? Or it's cosine. Is 2 an output of cosine? Is there an angle cosine of theta that's equal to 2? Well, no, of course not. Right? Because cosine is always in between 1 and -1. So that forces the domain of our cosine to be -1 to 1. Similarly with sine, the domain of arc sine is between -1 and 1. All right. So does that make sense about the arc functions, inverse functions? Essentially, it's just you input the values of sine and it outputs the angle. So I won't go through like the graphing of that. Just treat it as, I think that's the easiest way to kind of understand it is it gives you input like the lengths and it outputs the angles. So we want to think of it like in a triangle. Like if this was like 3, 4, 5, let's say, and I want to say arc cosine of 4/5 would give you theta, for example, because that is the angle that whose cosine is 4/5. Arc sine of 3/5, let's say, is theta, right? What angle gives you 3/5? It's whatever this is. So you essentially just reversing the roles of inputs and outputs. So I think the more interesting arc function is arctangent. So notice with arc sine and cosine, the domains are kind of boring, right? It's only -1 to 1. There's no inputs that I can do for arc cosine. However, that's not true for tangent. Arctangent, or let's say just tangent, has a nicer range. The range of tangent is, well, we know that by our limits. They have vertical asymptotes, right? And it goes up and it also goes down to -infinity. So since the range of tangent is infinite, that tells you that the domain must be infinite. So remember, the inverse functions are the outputs. So if the outputs is -infinity to infinity, that means that the inputs of the inverse function has to also be -infinity to infinity. So immediately already, that's pretty nice. So when we draw arctangent, we actually draw it on the whole number line. So how do you talk about arctangent? So similarly, we have to come up with an interval that works nice. So the interval for tangent, well, in the unit circle, right, I probably would not want to choose an interval that has pi/2, right? like I can't do 0 to pi, right? Because there's not really nice going on at pi over 2. And also, yes, so it's just like not continuous. So I probably would not want to choose that interval. But this one actually also, this one works, the one we did for sine. If I do negative pi over 2 to pi over 2, well, I have all these values of tangent that get hit, and by excluding these values here, so I actually should not be open but closed. By excluding pi over 2 and negative pi over 2, it means I don't have any range issues. So if I look at values between negative infinity to infinity, it will output an angle. So here's an example. Let's do arctangent of 1. What angle in negative pi over 2 to pi over 2 is such that tangent of the angle is equal to 1? So last in class, we actually talked about this, was pi over 4. It's the one like right here. The sine and cosine are the same there. Arctangent of 0. That's this one here, because sine is 0. Arctan of negative 1. Well, that's negative pi over 4. So you can do other ones like that, like arctan of radical 3 is one that you can do. And why is that? Because notice that radical 3 is equal to radical 3 over 2 divided by 1/2. So we know that sine of pi over 3 is equal to radical 3 over 2, and we know that cosine of pi over 3 is equal to 1/2. So that means that arctan of radical 3 is pi over 3. Similarly, if you flip it, arctan of 1 over radical 3 would equal pi over 6. So that's just the reciprocal of this. So you have 1/2 divided by radical 3 over 2. So cosine of, or sine of pi over 6 is 1/2. And cosine of pi over 6 is radical 3 over 2. So that's arctan. So I won't draw the arc, sine, and cosine because they're kind of boring, but arctan kind of, it looks nice. So one thing that's cool is that since we know that the limit as x approaches pi over 2 from the left of tangent is equal to positive infinity, then, I mean, this is something we'll do next class, is that notice that the limit as x approaches infinity of arctangent. The idea is that think about values that are getting close to infinity for tangent. So as x approaches pi over 2, tangent is approaching infinity. So that tells you an arctangent, as you bring x to be really, really big, that means the angles must be getting close to pi over 2. As you look at angles that are really small, the x values, the angles must be approaching negative pi over 2. So what's cool about tangent is that, by arctangent, is that it's actually bounded. the values of arctangent can never go above or below pi/2 and negative pi/2 respectively. So as x is going this way, the values of arctangent, the values of arctangent are getting closer and closer to pi/2 because tangent of pi/2 is infinite. And as you're going to negative infinity, what are the values of arctangent doing? They're getting closer and closer to negative pi/2, actually horizontal asymptote. So what's happening in between? Well, you know, arctan of 0 is 0. This region here is the first quadrant in the unit circle, because this is angles I'm plugging in positive numbers, and tangent is positive in quadrant 1. And this region here is quadrant 4, because I'm plugging in negative angles. So just remember, the only quadrants you look at for tangent are quadrant 1 and quadrant 4. So tangent is positive here, and tangent is negative here. So if I'm plugging in positive things, I have to be in quadrant 1. If I'm plugging in negative things, I have to be in quadrant 4. So it looks something like that. So there's only one 0, and that's tangent of 0. So this is arctan. So why, so when we, in class, when we talk about it, what's nice about arctan is that arctan is actually a candidate for squeeze theorem. So when I'll talk about arctan next time, or in class, because of this nice limiting property around pi/2. But so based on this, we can actually talk about like the limit with involving arctan, or I should say like 1/x or something. So like we can do this now. We didn't, I mean, if you knew about arctan, you could have done this then, but notice that arctan, we have 1/x must be between pi/2 and negative pi/2. So that means that negative pi/2x or pi/2x, and these limit to 0. So that must go to 0. So, I mean, so when we talk about that, you know, this will come up. And similarly, when we take infinite limits too, eventually, like of arctan of x over x, maybe, like we could do that using the squeeze theorem. But in class, we haven't even talked about what this means as x goes to infinity. So don't worry too much about that. Anyway, so that's what I have today. So just recall, we went through the sum angle formulas for sine and cosine. Well, not cosine, but I'm just gonna have to kind of work through that. I know it kind of follows from sine, but I forget how. And once you know the sum angle formulas for sine and cosine, then you automatically know the double angle formulas. And the half angle formulas follow quickly from the double angle formulas. And if we do another one, I may even talk about some other identities, like some of the power reducing formulas, which really, they are just double angle formulas, so not that important. But yeah, so that's all I have for today. And then we ended with arc functions. So we'll see arctangent more often in this class. We expect to draw. I mean, arctangent probably the only one is that like you should probably be aware of, just because it's nice. You can see very clearly the range. But like when we do graphing, I won't have a graphing with arctan. But I think just knowing that arctan looks like this would be very helpful. To remember that arctan is bounded. That's an important fact, that arctangent is bounded. Yes, any questions? Yeah, sure. Stop recording.